All right, so today we're going to be talking about heat capacity and specific heat. So heat capacity is a more generalized concept. It is the heat needed to increase the temperature of a material by exactly 1 degree Celsius. So that depends on the mass and the composition of the material. So this would be considered an extensive property, because it depends on the amount of the material, okay? We have another property that we're gonna more fluidly talk about is specific heat. So that's the heat that's required to raise the temperature of 1 degram of the substance by 1 degree. So this is now an intensive property because it articulates it's based on 1 gram. And so it's an intensive property that is based on the composition or the type of the material. And different materials are going to have different specific heats. So we're going to use this equation, Q equals mc delta T. Q is representing the heat, and it's going to be in units of joules. M is going to be representing the mass, and it's going to be in units of grams. C is going to be representing the specific heat, which is in a mixed unit, a combined unit of joules per gram degree Celsius. And then this delta T stands for the change in temperature. So your second temperature minus your first temperature. And that's going to be in units of degrees Celsius. So let's just try an example here. So it says a 15.75 gram, okay, so I'm noticing that that's going to be a mass, piece of iron absorbs 1,086.75 joules of heat, okay? That is an energy, so that's our Q. And its temperature changes from 25 degrees Celsius to 175 degrees Celsius. Calculate the specific heat of iron. So the very first thing that I want to do is I want to find my change in temperature. And that's going to be done by doing 175 degrees Celsius minus 25 degrees Celsius. Okay, when I do that subtraction out, my change in temperature is 150 degrees Celsius. Okay, so let's calculate the specific heat of iron. So I'm going to write my equation, Q equals mc delta T. And then let's fill in the information that we know. So we know 1,086.75 joules is equal to 15.75 grams times my C, which is what we're looking for, times delta T, our temperature change, which is 150 degrees Celsius. We're going to divide by 15.75 and 150 degrees Celsius on each side, and we're going to get our heat capacity of the iron as 0.46 joules per gram degree Celsius. All right, and so that's an example of how we would find the specific heat of iron. So let's think about this conceptually. If you take your hand and you feel the metal leg of your chair, and then you feel your tabletop, which is made out of more of a plastic material, what do you feel? What do you notice? So I notice that the metal feels cooler to me. It feels cooler to touch. Okay? So which material would have a higher heat capacity or specific heat? Okay? So because the metal feels cooler, it must be absorbing more energy from my hand than the surface of the desk, okay? Because of that, that tells us that it's absorbing more heat per gram degree Celsius, or more heat per degree Celsius, okay? So the metal has a higher specific heat than the material of the top of the table. So where we can apply this concept of Q equals mc delta T, or specific heat, is in this idea of calorimetry. So calorimetry is going to be a way that we measure the heat flow in or out of a system for a chemical or a physical process. And here in chemistry, we're going to talk a lot about our chemical process. So for example, we might have a reaction in this calorimeter. So our reaction will happen in the middle of these kind of styrofoam cups, which will insulate the heat transfer to the surroundings. And so all of our heat transfer will be measured by our thermometer, okay? So this setup is called a calorimeter, and it measures the when heat is absorbed or when heat is released. The key for this is that the heat that's released by the system will be equal to the heat absorbed by the surroundings. And so what we can do is we can set one of these equal to the other. So if the system is gaining energy, the surroundings would be losing energy. So we use a negative sign to just show gain and loss with our calculations. So the Q of the system is equal to the negative Q of the surroundings. So we could actually set mc delta T for one material, like water, okay, equal to another material, like iron, or like an actual reaction, and figure out the specific heat of it, okay? We are typically going to use water as the surroundings, okay? And the specific heat of water is 4.184 joule per gram degree Celsius, and that is going to be something that's super important for us, so put that at the top of your page and make sure you have that as a reference. 4.184 joules per gram degree Celsius. So let's try out a calorimetry example. So we've got a lead mass is heated and placed in a foam cup calorimeter. So we heat it up, it's hot, and we put it into our foam cup calorimeter. The calorimeter has 40.0 milliliters of water at 17.0 degrees Celsius for our temperature. The water reaches a temperature of 20 degrees. So our temperature goes from 17 degrees Celsius to 20 degrees Celsius, okay? How many joules of heat were released by the lead, okay? So the Q release of the lead is going to be equal to the Q gained by the water. Okay, so we're going to need the mc delta T of the water to figure out the heat released by the lead. So the first thing is our mass of the water, and that is given to us in an interesting way. It tells us the milliliters of water. What we also know is that the density of water is 1 gram per milliliter. So if we have 40 milliliters of water, we have our mass of the water is going to be equal to 40 grams. So we'll put that in for our mass, 40.0 grams of water. Our heat capacity of water is 4.184 joules per gram degree Celsius. And then the last thing is our change in temperature. Our change in temperature is going to be our 20 degrees minus our 17 degrees, okay? It's going to increase 3 degrees Celsius, okay? When we do our math out, we get a Q value for the release of heat by the lead of 502.08 joules. Notice our grams cancel out, numerator, denominator. Our degrees Celsius cancel out, numerator, denominator, and we're left with joules at the end. All right, thanks so much.